Welcome back, folks. We're going to talk about power. We're talking about how much energy it takes to move charge around, and if we want to do it in a timely fashion, then we can't neglect power dissipation. A lot of components that you're going to go buy have some power rating on them that you can't exceed. So we want to make sure we're staying below that. Otherwise, you're not going to have a circuit. You're going to have an ignition source. It's usually where I talk about my dishwasher catching on fire a couple of years ago. See, you miss out on all those good stories. My dishwasher caught on fire. Somebody didn't check the power rating on a component, and it wasn't steam coming out. It was flames, smoke. So that was rather fun. Dishwashers, you don't think of as being the appliance that's going to catch on fire. Check your power rating, and here's how we're going to do it. Let's see. Let's get our picture up here. So power, check it out. Okay, so think back to power from your physics classes, and we're going to define it as the amount of energy that's dissipated per unit time. So we may see that as lowercase p, and the amount of energy, we can talk about how much work we do for some period of time. So it's the time derivative of the work being done in a system. Okay, so we want to figure out how to get to how much energy is being dissipated per unit time in an electric circuit. And we've talked about voltage and current. Resistance plays into this a little bit. I'll talk about that in a moment. But we want to think back to our definition of voltage. Okay, is how much energy, that's a junky W, how much energy is required to move some quantity of charge. Okay, and our definition of current, it's the flow rate of charge, right? So how much charge is moved in some period of time. Okay, so if we put all of that stuff together and we say P equals our work done in a period of time, and we can get that back out by taking our voltage and multiplying it by the current. Okay, and the amount of charge ends up not mattering. It drops out of the equation, and we're left with the amount of work over the amount of time. So we can correctly say that power is simply voltage times current. Okay, I wish it was that simple. I wish we were done, right? Short video, we're good. But it's not that simple. We've got to think about the passive sign convention as well. Which direction is the current flowing? Are we supplying energy or are we dissipating energy? And we can determine that based off of the passive sign convention. But P equals VI, that's an important one. Okay, and we're going to consider passive sign convention. Let's do that one first. I think I want to do passive sign convention first. Okay, so we're going to assume all components are passive when we're calculating power. So assume the component is passive. Okay, and with an individual component, we're going to look at the current direction, and we're going to assume a sign for that current direction. So let's say I have a resistor. I put a voltage across it, and what do you want to call it? This is usually where I pick a random number. I have you pick a random number, but you're not here to pick a random number for me. Okay, so 10 volts. Let's say we put 10 volts across it, and 2 amps is going to flow. And let's make 2 amps flow in this direction. Okay, if I want to calculate the power being dissipated by this resistor, I'm going to say the power is whatever the voltage is, and then I look at the sign, and we have to say, is that flowing in the positive direction or negative direction? So according to the PSC, passive sign convention, according to the passive sign convention, which direction is the positive direction for current flow if the voltage across this passive element is 10 volts, plus on top, minus on bottom? hopefully by now you're yelling at your screen that the positive direction is down. Okay, the positive direction is going to flow this way. Okay, and this is the positive current direction. All right, that 2 amps is flowing down. It's flowing in the positive direction, which is great. Okay, so we can come over here and we can say this is plus 2 amps. I wrote the plus just to be absolutely explicit in what I'm doing here. And we can go through and multiply it, and we're going to get 20 watts. Okay, it would be joules per second, right? But we're going to go with watts. Okay, so 20 watts, and this always answers the question. If you abide by the passive sign convention, then you're always answering the question: how much power is this element dissipating? Use the passive sign convention to answer the question. How much power is this circuit element? CKT, I think that's the first time I used CKT. It's an abbreviation for circuit. It's a strange abbreviation for a circuit. My professor has used it on me. I'm using it on you. Welcome to the inside of my brain. How much power is this circuit dissipating? Okay. How much is it using? Okay, if we look at the passive sign convention, we're always answering this question. Okay, so this resistor is dissipating 20 watts. All right, so let's get a voltage supply. Okay, and let's say it's a 10 volt voltage supply. Let's keep the numbers simple, but let's say that 2 amps is going up. Okay, even though it's a voltage supply, it's not a passive element. It's adding energy to the system. Okay, so we'd say it's an active element. We still assume that the positive current direction follows the passive sign convention because we want to answer the question: how much power is this circuit element? Oops, I forgot a word. Element dissipating. Okay, so let's look at it in this case. So positive on top, negative on bottom, we're going to get the same positive current direction. Okay, positive current direction. So when I go to calculate power in this case, I'm going to say the power being dissipated by this circuit element is 10 volts. And I'm going to take that 10 volts no matter what its polarity, but I'm going to look at the current. Positive current direction is down, the 2 amps is flowing up, so now I have negative 2 amps, and we end up with negative 20 watts. Okay, so how much is this voltage source dissipating? Well, it's not actually dissipating, it's actually sourcing current or supplying current. But if we wanted to answer the question, how much is it dissipating? Well, it's dissipating negative 20 watts. Okay, so this would indicate, that sign right there indicates an active element, not a passive element. Okay, right now the only passive element we've talked about are resistors. We're going to talk about capacitors and inductors later on in the course. But this voltage source is active. It's supplying energy to the circuit. Okay. So passive sign convention needs to be respected even when we're calculating power. So here's my issue with a different way to calculate power that comes up. So other ways to calculate power. Okay, very commonly we may take a resistor like this, and we say we know the voltage across it, we know the resistance, and we want to find the power dissipated by it. And we can do that. We know P equals VI, okay, but we don't have I calculated explicitly. So we come over here and we say, well, I equals V over R. And we use Ohm's law to calculate I. Perfectly reasonable thing to do. And we plug it in, right? So plug that in up here. So take all of this and plug it in to that, and we get P equals V. I'll use a bracket, V over R, okay? Or we can write that as P equals V squared over R. You're going to see that a lot. Here's my problem with that. The voltage was, you don't take the sign with the voltage, but you have to consider current direction. And when we use this form, we're losing the sign from the current. We lose that sign from the current because we end up squaring it. And whatever sign was there, it's gone. Okay? This is commonly used. I'm going to use it occasionally, but you've got to be aware that this only calculates the magnitude of the power, not whether it's being supplied or dissipated. Okay, so only finds the magnitude of power, not the sign, which is going to indicate whether it's being supplied or dissipated by the element. Okay, there's a similar one if we have I'll draw it sideways just for fun, my kind of fun, not your kind of fun. If all we have is the current and the resistance, you may say, well, I want to find the power, P equals VI, and we can use Ohm's law again, right, because we need to find V equals IR. Okay, take all of that and plug it in there, and we run into the same problem, but you are going to see this form of power calculation. P equals IR times I, or more commonly written as P equals I squared times R. Okay, only finds the magnitude of power. Same problem, right? We're squaring I. We've lost the sign on one of the factors in that equation. So we've got to be careful with this. It's useful. I use it. I'm not going to pretend I don't use it, but I also know that it has a limitation. I don't know whether it's being supplied or dissipated when I calculate it this way. Okay, so next video I'm going to take a problem and we're going to see that it's really important to do this. Okay, depending on the way the circuit is laid out, it may be necessary to have supplies that are actually dissipating power. You can't look at a voltage supply or current supply and say that's supplying power, because the rest of the circuit might be forcing it to dissipate power. So I have a little example circuit that I'm going to kind of run through the calculations with you, but I'm going to break that out into a separate video. Okay, so stay tuned and good luck.